Good morning. Can everyone hear me and see my screen?
Yes, sir.
Yes.
Yes.
Hey guys, how you doing? We had a long break, didn't we? It's good to see everyone back. I have one question. I have someone in the chat who is very nice, but your name says Dolores. Who are you? You can let me know in the chat if you can. Ah, Roberto. Gotcha. Okay. Thanks. That works just fine. Just wanted to make sure I got you down. Okay, guys. Let's see. Yes, it's a pleasure to have you back too.
Hi, good morning.
Good morning. Good morning. I have another person that has just entered the room. Let me know either in the chat your name so I can see what computer you're using and make sure I get your attendance. Hold on a second. I'll tell you who you are. You're showing up as a capital CAS score 0. Who is that? Who do I have with us? And if you need a minute to get settled, that's fine. I'll come back around. I just can't put you down for attendance till I know who do we have here with us. Okay, guys, let's give everybody just a couple more minutes on attendance. I'm going to pause my mic for a moment. I am John Rodebush. This is Wind Mechanical, as you can see. So if you're supposed to be in a wind course, you're in the right place. I generally do not do video just because I live out in the country. Oftentimes I'm going from home and my internet's not the greatest. But I will see you guys all next Wednesday if we have not met before. But I know most everyone in here. So let me do a few more on attendance and we'll talk about what we're going to do. I'll be right back.
Okay. All right. Okay, there we go.
Good morning. Is this Landon?
Yes, it is. How you doing this morning?
Hi, Landon. I don't have a camera on. You're more than welcome to leave your camera on. We usually we don't. If you don't want to, you don't have to.
Okay.
I just wanted to know where you are.
Yeah, absolutely.
See everybody.
Yeah, I'm actually on campus this morning. I didn't read my email until this morning.
Yeah, I'm sorry about that. Yeah, are you okay?
Yes, yeah, I am. I'm in the break room. I'm comfortable, so yeah.
Okay. You could probably go. You could probably go in one of the computer rooms there on campus and get online if nobody's in there. You know.
Okay.
Yeah. And just kind of see, or I don't know what to do. I guess you're kind of stuck in a place. I am recording this.
Okay.
Great. So, you know, you and I haven't had a chance to meet yet and talk about anything and get into like how we're running the classes. So let me just kind of get into that, and then you just kind of hang with us. I guess you'll be all right.
Sure.
Okay. All right. Let's see. Who am I missing here? I don't see Josh. I got Landon. I don't see Christian, and I have a feeling Christian might be on campus too. I don't see Christian Garcia. Okay, so that's where we're going to stop, I suppose, and we'll go ahead and get started with the class. So let me go to our home page and let's just talk about what we're doing. Today is the first day. And you know, what I'm trying to do is just give us a chance to have some discussion. Too often when we're doing our lessons together, we don't have a good opportunity to engage in some of the questions and in some of the content. So today's going to be a little bit different, and I'll kind of explain like how I'd like you guys to set up the class. So you can just listen, or you can work on your assignment while we go through this material together. And then you know, in your case, Landon, I think you're kind of stuck, but you can kind of follow along and work on the stuff later, and you'll still know what we did.
Okay, great.
Yeah. So let's go ahead and look at how the class is laid out. So when we look at our home page, you're only going to see week 1. So you're going to see that we've got a lot of changes coming to this course module. We have some new trainers coming in, and they're still ordering our computers for those trainers, and those trainers are still getting set up, and we're ready to go. So I don't know how much of the trainer integration we're going to have in this class. We'll definitely be messing with them, but for right now, we're just going to get up and get going like we always have. And so for an easy lesson to do virtual, we do it virtually on Mondays. So for those of you guys that are confused, you normally, and if you're not confused, you understand, we normally run classes on Mondays virtually, and then Wednesdays we're on campus. So, you know, if you went to campus and that's what you knew, you were correct. This first day is just a little bit either. I was getting a lot of questions and a lot of confusion, so I decided just to do our first lesson today virtually and get us going. We were going to go get into our climbing gear right away. So the first day of class is going to be next Wednesday, which should be like January 26th, I believe, when you would need to be on campus for this class. Let's see here. And you know, what would I be doing? Well, we're going to be getting our harnesses on. We're going to be doing climb training. We're going to learn all about our harnesses. So we'll be busy all day working on that during class time. And we'll be doing that for the next couple of Wednesdays. And then in between there, we'll be working on trainers while we're there on Wednesday. On Mondays, we're going to be just going over this material together and trying to learn more about wind turbines and get you ready for your tests and help you get through your homework. So what I want to show you is our syllabus. Of course, if we click on that, the easiest way is to just click on it and open it up. And I'm not going to spend an enormous amount of time on this because these things are the same thing you see all the time. Class starts the 19th. The 13th is when it ends. This is the name of the course. And so what we're going to be doing, this is my information in here that you're looking at. And the times that you need to meet with me are, the times of this class are Monday, Wednesday, 8:30 to 12:30. And my office hours are Tuesday and Thursday. So we'll go through the information. On the very back of the syllabus, you'll find that we're going to be going through class introductions and looking at GE turbines today. So we'll reference the syllabus back and forth, but I really don't want to spend all morning talking about the syllabus. Right here on the right side, you can see how the grades are going to be worked out. So your homework is 20%. It's a very easy course, 90, 80, 70, 60 on your grades, A, B, C, D, just like any traditional class. And professionalism and labs, you're going to have some things that I'm going to label as labs. And that's going to be, say, you show up on Wednesday and you're there climbing with us, you get 100 points for that day for being there on your lab. Okay, so it's part of your attendance on those days when we click you in there. If you're missing those days, you'll see your professionalism in your labs go down, because those Wednesdays are important. Now we can work on schedules. If you get into a problem and you're not able to attend a Wednesday or something like that, it's not going to destroy your grade, right? But you really need to try to make it to as many of the Wednesdays as we can. Now on the Mondays, we're supposed to be here together working and learning, and I highly recommend it because I generally try to go through your homework with you, and it does depend on what we're doing. Some of this stuff is really hard, and I do record videos, and I will post them to our YouTube page as needed, and go from there. So you'll be able to review the videos, and you'll be able to see some of the stuff that you might have missed. Projects are just going to be things that we talk about. Projects generally are going to be some type of career-oriented assignment where you're either going to be looking at a type of component and doing a report on something very interesting, like the largest wind turbine in the world, or you might be looking at just the drivetrain of a certain type of wind turbine, and that may not be really what you want to do. Another type of project that we may do will be more of like, where do you want to work? Which one of these companies is the company that you want to work for? Those are usually what the projects are for. It's a chance for you to do a little career research on the places that you want to work and the jobs that you want to get. We also sometimes will do things on campus where we may need to do a little work. We've got some things that we can play with more or less and turn into projects. So those projects, there's only going to be a couple of those depending on how this class flows. So I'm not going to assign any of those right out the gate. You do have your regular pre-tests, which is like a quiz of your midterm exam, and your final pre-test, which is like a quiz of your final exam. So it gives you a chance to get ready for those. Okay. Is there any questions for me so far?
I personally can't think of any
Okay.
right now.
No problem. And I'll just keep going, and then we'll start to get a better idea of how my classes flow and then what you need to do. So let's next take a look at, now if you were confused, I think everybody saw the announcements. You want to watch the announcements, because that's about the only way I can get a hold of everybody without trying to just call everybody on the phone. So I don't do a lot of announcements, but I would always say just check announcements before your class, and then you might see something change. Like my internet may go out and I may not be able to run class, or my car may break down on the road. So you still will show up and then I won't be there. I try my best to at least get an announcement as soon as possible as what I know I need to do. Okay, so if you click on home, we can go ahead and get started on the lesson. So what you'll see is simple. If you click on home, you see week 1. That's all I've got open. That's all you got to really worry about. Work on your module 1 for week 1. And I kind of consider Monday part of week 1 a little bit, because they're starting us on Wednesdays and it's messing everything up. We should be starting on a Monday, but we're starting on a Wednesday. So we'll just have to adjust. Now, I think what we can do is let's go ahead and look at this here. This says module 1. It says Introduction to Wind Turbines and Competent Climber Training. So you can see we're going to look at really, it's just a brochure. And I've used it for years. And one of the reasons I like to use it is because it's a nice way to do a little introduction to GE wind turbines, very specifically. So the idea and the purpose is to familiarize yourself with it, because some of the other stuff that we're going to be getting into is going to seem pretty complex. And I don't want you, some of you I know don't know anything about wind turbines at all. And so you're going to be thinking, okay, what is what? And so what I like to do on the first day is, if we're on campus, we do this as a big group, and we're just going to do this as a group together. And I want to try to get a little more engagement out of you guys, instead of just reading things to you when we're in our virtual time. So what we have is a submission that goes along with this. So let's go ahead and continue to look down throughout this information though. So today we will go over this technical document, and then there will be a worksheet that you need to fill out. It is in a Word document form, so you can download it to your computer and type. Or if you want to print it out, you can print it out and write it in. And then what you have to do is upload either a photograph of your work, or you got to upload the file as a submission that you've got that done. So this is a fill in the blank. So when we do this type of activity, it's a little bit better if you can try to do it along with us. If you got a piece of paper laying in or something, just write down your notes, and you'll be able to kind of fill that in next time, or you could probably turn that in, honestly. Let me know in your situation, but it might be better to go back through it later.
Okay.
But I'm going to go over the homework with you guys today, and we're going to talk about the information. So I'm going to more or less read a paragraph of something to you, and then we're going to have a couple questions about it, and that's part of your homework. And the reason why I want to do it that way is because it gives me a chance to just kind of start to open up some conversations with you guys over how these wind turbines actually work, without just hitting your head real hard with a bunch of technical specifications and a bunch of technical documentation. And then you're looking at all these different types of components that look terrifying, like, how do I even work on that? Oh my gosh, we're not trying to do that to you right away. What we want is, think someday you might be a wind tech and you're going to sit down in an office, and if you were to read this brochure about the brand new wind turbine that's coming out that you're going to be working on, that you would even understand the brochure. If you can't even understand the brochure, then you need, you got a problem, right? If that's what, so that seems silly. Another way of looking at it is to talk more fluently about a wind turbine, understanding it from top to bottom and in a more holistic way. And hopefully that's really a good conversation for us to have, because you're going to get into an interview at some point with someone, and then you're going to be talking to them. If not, you're going to be talking to other techs about some of this stuff. So, and then if you, and I see we got Edwin here, which is good. I see that you made it back. But if you're working on other turbines, like Vestas turbines, you know, looking at some of these GEs is going to be neat, because you're going to be able to see the differences between them. And mostly we're looking at the GE wind turbines, because those are the American-made wind turbines, and they are one of the most common turbines in the United States, if not the most common turbine, and very common around our area as well. So there's a couple different versions of them. So when we try to learn about how a wind turbine works, it's good to pick one and really try to focus in on how that one really works. All the others are going to work similar to it. And they'll have different gearboxes. They'll be taller. They'll have maybe transformers at the top of the tower instead of the bottom of the tower. But at that point, you now are able to understand a little bit more about what it is that a turbine is doing. So the next section is something that we'll be working on probably Monday. It's in your module 1, but I have it there for those of you that want to know what else we're going to be doing. We're not just looking at this GE brochure. That can't be all, you know. Well, you'll find out when we get into that. There's a lot of information in it, but you'll also find that it's not too much, and that's kind of the point. Then you have this module 1 right here, Competent Climber training book that we have. That is really what we're doing. So when you become a wind tech, you've got to go through competent climbing training. And you know, I'd say most of you, and some of you have actually been in a wind turbine, but most of you have not been in a wind turbine or have no idea. So we're going to be just going over the basics on wearing your harnesses and practicing ropes and rigging and rescue training and rappelling down the tower and demonstrating things. If you know you're really weak in one of those areas, you'll find it's pretty fun. So we're working on that stuff as a group, and when we do that, we'll do that in Griffin Hall in the manufacturing lab. And that is room GH178. But we'll always meet at the Energy Center for this course first, and then we'll move on down to the other lab, just to avoid confusion, because we're not always going to be down in the manufacturing lab all the time. Is there any questions so far?
I got a quick question.
Yeah.
Will there be an opportunity to be selected by one of the companies prior to graduation?
Yeah, it depends on what's going on. So, you know, what happens is the wind farms will call and they'll be looking for people, and generally they want someone who's almost done with graduation. But with the way that we run classes, with you only needing to be on campus on Monday, I'm sorry, let's say that right, on Wednesday,
Right.
and they know you're going to school, yeah, they'll let you start the job and then you can still go to school. I mean, that's one situation we've got going on in this class right now.
Oh, well, okay, great.
Yeah. So the thing about the competent climber rescue training thing that I want to talk about is there's really no perfect competent climber training that we can do, because most of these companies are going to make you take their competent climber training no matter what. My goal is to help you look and feel like you've already gone through it, and that you have a better understanding of how to wear your safety gear, your PPE, which is a very, 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 very big part of wind. And then also, I mean, if I'm going to put a rope in your hands, I'm going to say, I need you to tie this bag with a bowling knot or a clove hitch. I need you to tie this cable with a half hitch and pull this up the tower, or do some rigging on some stuff. And most of the time I find, you know, if you've been in the military, you probably have a pretty good idea how to do knots. And then I'll be like, okay, you're good. But most of us, we don't even know how to tie rigging knots right. And we got to learn how to do that. So I'll be putting you up on our little tower. It's a very short tower, 10-foot tower. It's designed to just put you under stress while in a harness, not to where you can really fall and get hurt. But it's high enough that you're up there, and you get up there, and then you've got to work while you're on this tower. And I'm going to be asking you to do things while you're trying to, and that's going to give you a really good idea of what it's like when you're working in a tower and you have no idea how to do any of the stuff or how to tie off. It just helps ease that in. So we're going to go through a fall protection program, and there is 2 assignments that we see in here. We got assignment 1, which is this lab worksheet, which we'll look at shortly if you haven't already seen it. And then you have this, that's your assignment 1. We'll want to get that done by next Wednesday is the goal. So it does have a due date. I do accept late homework because I know some of you are working weird hours and it just happens. So you just turn it in. You got to get it into me, but it does have a due date, so you know if you're getting behind. You have a lab 1 fall protection training worksheet that we won't get into today, but we'll be able to get into on Monday. And that's going to get us all prepped and ready to go for Wednesday. And then we'll be talking about some of these knots, but knot tying's better in person. So the rest of the stuff it's in there. When it comes to the knot tying, if you can get yourself just a little piece of rope and just start practice tying knots, that's kind of the best thing. We'll all have some rope that we'll be working on, and I try to bring in some rope and cut you guys some little pieces so you have something to tie and practice your knots on. And you're just going to have to at some point demonstrate to me that you can tie those knots to complete that learning activity, which would be part of your lab grade. Okay. And then we have just some extra information in here for those of you guys that are hungry for more. This stuff's too basic for me. I want to know more. So I always try to throw in some stuff in there that I say explore. Take a look at this stuff, and we'll take a look at some of those things. So let's see here. So what I want to do is I'm going to pop out of this, and you're going to see the module there in a different format, but you can see how everything kind of flows the same way as what we were looking at. You'll see when you look at the module like this, you'll see assignment 1. Well, this is the book that you need. So you're going to want to open that up. And I think I already have that open. Well, I have the homework open right there, but we'll go back 1 page. Slide down, just go to the previous page. And you'll see the document. Open it up. You're going to notice a lot of the stuff I use is old. And part of the reason is most of the wind turbines around here are old. You know, there's a very good, they were built in 2006, 2007, 2008. And then for a good 10 years, they really didn't build very many of them. And now they're starting to build some more new ones. But there's a really good chance that you're going to get on one of these wind farms and you're on an older turbine that's 15 years old. And so that's kind of what we look at. We start with the basic GE, and we kind of look at the old documentation of the turbine because they don't make them anymore. Okay, so one of the things that we want to look at here before I get too far off is let's just ask this big question. Does anybody know what is the biggest and most powerful wind turbine out there?
Are those the offshore wind turbines?
Yes, they are the offshore wind turbines. And those are generally in the high megawatt size. When I have a little thing like this, let's click on it. Now, I think Vestas has one that's coming out. Edwin might know if you pop in there and let me know. Coming out maybe later this year that's going to be bigger than this one. And I think it's, so sometimes this stuff doesn't work, but if you just click on the link, that is the biggest one that is out there right now. And the ones that are onshore are not as powerful, but these could easily be built on site. So there's a nice little video of this. Let's go ahead and let's take a look at that. Let's watch that. That's fun. So this is just showing them build this wind turbine. This is the biggest one in the world. Now you can see that this one is actually on land, but it can be on a floating platform like this. There's different ways that they put them out in the ocean, but this one is a prototype. And whenever you see these wind turbines built, and I used to build them is what I did, and you go out there and you work in the field, and the iron workers, they go out there and stack them out with these enormous cranes. Now, does anybody know what that turbine doesn't really look a whole lot different than the other turbines that we have around us? But what do you guys think is the difference between this one and the ones that we have here?
Is it the blades?
Well, blades, yep. What about the blades? Anything? It would be length. They're bigger. So they got a much bigger swept area. They're taller. And they got a much bigger generator. So bigger means more power, but they're not that much bigger. But one of these wind turbines makes as much power as 10 to 14 of ours that are around here. Think about that. 10 to 14 wind turbines. If we start building these larger ones, we won't have as many wind turbines all over the place. But that's off down the distance, but that's what's coming down the pipeline. And so this thing is 14 megawatts, which is the GE that we're looking at that you probably will be working on is just a 1.5 megawatt. So there, that's showing you the difference there. So that's just a little information to feed your head.
The new Vestas turbines are the V236 15 megawatt.
That's it. And I don't know if they've got a prototype built yet. I was thinking it was going to be 2022. Does anybody know if they've got that one out yet? Yeah. Well, and you know, these things are so powerful. If you were to sit on top of them and just count how many times the blade goes around, I mean, if they're just spinning their blades, I mean, the thing's making up to 14 megawatts an hour. You know, that means it's powering, you know, a house in a day in like 20 rotations. 20 rotations powers one house all day long. It's just amazing how powerful they are. So the next area that I want to see, make sure you see and understand is, so this is what we're going to do today. So we're going to go through this book and get that done as much as we can. We'll see how we are on time. When you do a blended class, these are blended, that you're supposed to be 1/3 of the time synchronous. That means 1/3 of the time you and I need to be seeing each other, which we should be able to see, you know, on Wednesdays, and then I'll see you most of the time in this portal. Let's see, I've got it. Message. Yeah, you guys can so I just want to remind everybody that the video is being recorded. So if you do have to step away, just remember, you'll be able to go back and watch it later. The next section is the fall protection training course book. Now, these things are black and white because they're designed to be printed black and white. And so you don't have, if you want to print them out as a little book, you can. If not, you can use them digitally. Just black and white's a little uglier than color, but nobody wants to print 70 pages of a color book or anything like that. So that's up to you, and I doubt that you want to do that. But the fall protection training is from DBI Sala, which is a very, very, very good. It would cost you, I think it's like $2,400 if you were to try to take this yourself. That might have been a while ago. They've changed things, but it wasn't cheap. And your employer, that's why your employer generally just does your own rescue training, because they don't like to pay these people all that money to do this. But I went through this training years and years ago because that's how they had to do it. We go through this training for all the reasons I said before, and you have a worksheet that we'll be looking at together. So we most likely won't start this today. You can if you like. But if you want to hold off, your main focus would be to first get your lab book open, because we're going to read through it, and then I would download this worksheet and get it set up so you can start typing it in. As I go through this book, you should be able to answer some of the questions. I'll ask some of the questions out loud and just give you a little discussion about them, and just make sure you guys understand some of the stuff. And we may only get so far in this as well, because, you know, the whole point of this is to have a little bit of a discussion. Okay. So this is the actual technical document right here. Okay. And it's only, see, it's from 2006. I'll blow it up a little bit bigger here for you. It's only like 18 pages long. It's not very long at all. But the information in here is what we want to talk about. Okay, just kind of go through a nice slow understanding of what this wind turbine is, what it does. Let me back out of this. And then let's look at the next. This is your worksheet. So it's 6 pages. So there's a little bit of work here, but it's easy because everything is it's in a linear fashion. So when you are answering this first question, that's in the first paragraph. You're not going to have these questions thrown all around you. You're just going to read the paragraph and you're going to fill in the blanks. And what I would do is just write the answers right down below this. Type them in there as we go along. And you'll see that I have questions numbered to a certain point, and then it'll say part 2, just to give you a break from the questions and make sure you're not lost. So at this point, you should be looking at section 3.8, 3.7 in that brochure that we're going back to. So that way you're like, oh, I can't find the answer. But we should, what we're going to do is go over all of these questions today. Okay, I'm sorry if I'm going too fast. There's a part 3. And then we're done. And that's all we're going to worry about today. And then, you know, in Monday's class, we'll start the competent climber training, and we going over those questions then too. And then Wednesday is going to be a hands-on day. Okay. So if you can't download this, I'll be reading the questions to you out loud. You can kind of see back and forth where we're at. I'm going to mainly be looking at the documentation while we go. That's what you're going to see on your screen, but I can see the questions and I'll be reading these questions to you. So let's just go ahead and just get started. And if you don't, like I said, if you don't have a way to download anything, but you got a piece of paper and pencil, just kind of write down some notes. That would be one of the best ways to do this. So let's first familiarize ourselves with this. So we're not going to be doing this for 3 hours either. You know, I generally lecture for about 2 hours tops. And then I try to give you time to finish up all this homework. So we're at 9:13, so we'll probably be done around 10:30. Okay. And then that'll give you a chance to try to get that done and get it submitted in. And then you're done for what you got to do for this week for this class. Okay, so the introduction says this document summarizes that as big as I can. This document summarizes the technical description and specifications of the GE 1.5 60 Hertz wind turbine generated system. All right, so the first question on your lab packet is, what frequency does the GE 1.5 run at? Does anybody know?
60
hertz.
Yep, that's what I want to hear from you. What other frequency could it run at? Does anybody know? $50 hertz. That would be if it were running in Europe. But because this is running in America, we run on 60 hertz. That means 60 cycles per second on a electrical waveform. So we don't want to get into that too much. Let's move on to the next section. So it says the GE 1.5 60 hertz is a 3-bladed upwind horizontal axis wind turbine with a rotor diameter of 77 meters. Okay, that's a lot in that question. So the next question is basically a repeat of that. We can tell that the wind turbine, so the GE is a 3-bladed upwind horizontal axis wind turbine. What's the difference between an upwind and a downwind turbine? Do we remember?
I believe it depends on which way the wind blows. If I think an upwind blows through the blades and then hits the
Yes,
generator, and then a downwind blows, hits the generator, then through the blades.
correct. Yeah, so Tyron explained it exactly. So downwind is like the blades are behind the turbine. Upwind, the blades are kind of in front of the turbine, or as Tyron explained it, which he did a good job. And horizontal axis. What other axis is there? What are they talking about there?
The vertical axis.
Vertical axis, correct. So we've seen the other type of turbines. They look kind of like an egg beater. Oh, that's good. So all that means you guys are retaining some of the information that you've already learned. Now, if you've never had this information, now you kind of have a little bit better idea that there's different types of wind turbines out there. And this one in particular, and all of them are going to be upwind horizontal axis wind turbines, just to help you out a little bit. We don't do downwind horizontal axis turbines very often. And one of the reasons is because the pole. So the next section is about the pole. It says the turbine rotor and nacelle are mounted on top of a tubular tower, giving the rotor hub height of 64.7 meters or 80 meters. So what do they mean when they say rotor hub? What is that? Rotor hub height. Let's look at a picture. There's a picture of a wind turbine. There's the ground. So that means this tower is 80 meters to the center of the hub, not to the top of the blade. Now the blades are 77 meters. So 77 meters means that is the diameter, rotor diameter. And so if you were working in the field with some people, they may say that the turbine is an 80-meter tower, or 80-80 or 80-100. And that just simply means the difference between the hub height and the diameter. All right, so let's move on to the next section here. All right, so we know that they're 80 meters, which is roughly like 250 feet, 240 feet tall is how high up you are when you're sitting on top of this thing. And they get bigger. You know, they can go to 100 meters. Usually around 100 meters is about as big as they go when they're on land. All right, so the next section says the machine employs active yaw control designed to steer the machine with respect into the wind, active pitch control, and generator power electronic converter systems from a speed variable drivetrain concept designed to produce the nominal 60 hertz at 575 volts. Boy, that's a lot of stuff right there. So what you want to do in your homework is you want to type in on number 4, it says the wind turbine employs active yaw control. What's the difference between active and passive things? Does anybody know? We're talking about like a wind turbine. I'm trying to get you guys to just a chance for you to hop on in there and just shoot from the hip It's okay.
I believe it
Um,
means
Go ahead.
with yaw control that active is like the turbine itself is turning in a cell, and passive is the wind is doing it.
Yeah, active. Anybody else want to add to that? Yeah, that's good. So active is meaning that we have a motor. We have a motor that's turning the turbine. The wind isn't blowing the turbine. The motor is turning it, something jawing it left or right. So
Mhm.
this thing's controlled by robotics. Okay, so we know that this is just a big giant robot. So the wind turbine employs active yaw control, active blade pitch, which is going to mean the pitch is changing this direction or that direction. So question number 5 is basically wanting you to explain this, you know. So it means that the machine is controlled by motors, turning the nacelle into and out of the wind. The power converter, that's what allows the generator to turn at speeds faster, producing a higher frequency than 60 hertz. This is a little confusing, I know. But we've got a power converter that corrects this with an inverter, with electronics. They call it pulse width modulation or digital frequency correction. But what that does is, in number 4, if you're trying to go like, what does all that stuff really mean? That stuff means that by having active yaw control, active pitch control, and a generator with a converter system and with a variable drivetrain, it means that this turbine can produce power at a variety of wind speeds, not just one wind speed. So one of the things that we have to ask ourselves is how much power can this thing actually make? And that's just based on how much wind we have, as we know. But part of what happens is all of that is working together, closely together, so that it is able to maintain the most perfect speed that it can to capture the wind. We'll talk about converters and different converters and some of the different things there that will create some of this, what I call magic, that's difficult to understand at our level. But what we can understand is that we need our blades to pitch and turn when we want them to turn to chase the wind. And it also means that we're going to need to understand a little bit more about inverters, rectifiers, and converters to have a full understanding of how it's able to take that wind at different speeds and create 60 hertz. That's the trick. So that might be a little bit much for you to understand entirely at this point. There's a mouthful of stuff in that one paragraph, but let's just move on. That's what we're learning, how this turbine is doing that. So one moment. Okay, I'm back. So the next question is, list the main drive components according to the handout. So this next section simply talks about the major drive components. You need to just write down main shaft bearing. We're going to learn what that is. The gearbox, the generator, the yaw drives, YAW drives, and the control panel. Those are all the main parts of your drivetrain system. So they work all together in tangent to try to keep this wind turbine making power at a variety of different speeds. Okay, so we know the number 7. I'm on number 7. You guys should be on number 7. Just all that's saying is how large is the rotor diameter? The rotor diameter is 77 meters. Any questions or comments so far? This picture's terrible. We don't have any questions that come out of this picture. So we'll look at a better picture. So just kind of ignore that one there. Can't read it anyway. Okay, so we know the rotor diameter is 77 meters. They give you a fancy number called a swept area, which we'll do some calculations on what that means later in the year. But the next question is, how many revolutions per minute is a rotor designed to spin? So what are they calling the rotor? Does anybody know?
The
The
rotor,
ro- yes.
the middle part of the, it's basically the thing that when the blades spin, it spins the rotor that's in the middle of the wind turbine.
Yes. So when I think, then you're right. And so that's called the hub or rotor hub. The rotor is more or less the blades and the hub, the propeller in an airplane and the nose cone, that type of thing. But we call this the hub. And, you know, we call this the airfoils. These are the airfoils or blades, hub, but this whole thing is the rotor. This whole thing right here is the nacelle or the nacelle, depending on where you're from. This is also, this part right here is called the hub. And inside that hub, we can see a little pitch motor there. Okay. So it's designed to operate between 10 to 20 RPMs per minute. So when we look at these wind turbines, they're spinning in a certain direction and they look like they're going really slow, but they're going as fast as they're supposed to go. And we know those blades are moving depending on the speed of the wind. The blade tips will be hitting around 150 miles an hour. So they're moving fast. The next question is, what is full blade pitch angle? 90 degrees, right? So what we need to answer on our blades is there's a couple terminologies. Full blade pitch angle is approximately 90 degrees. And then there's an angle called the 0 degree position for your blades. So when we think about it, think about a blade being able to spin in a circle. Where is 0? Where is 90? Okay. And so the blade isn't going to necessarily spin in an entire circle. It's going to spin up to its limits. Each one of these blades will have a limit switch that'll allow it to spin roughly 90 degrees. So full blade pitch angle is 90. And then 0 degrees is, well, what they call the airfoil or the blade is flat to the wind or flat to the prevailing wind. Prevailing wind is just the where is the wind coming from? The next term is important because it's a weird one if you don't know what it means. What does feathering mean? My blades are feathered. What does that mean? Well, it means that we are breaking the wind turbine. Not breaking it, but breaking it like in brakes.
Yeah, usually when I get up tower, I'll have to mess with the controller and feather the blades so I can pin out the blades, lock it out.
Yep. How many pins do you do?
It's 3 pins.
That's
Because
what it should.
I'm working on the 150 4 megawatts. That's what they assigned me to.
Oh, wow. Those things are 4 megawatts.
Yeah, they have the V82s and then they have like the 110s, the 136s. I've been in all of those, but I've just been mainly doing services on the 4 megawatt 150s.
Awesome. Very good. Very good. Yep. Excellent. So now for those of you guys know, full feather just simply means a blade rotation that incorporates aerodynamic braking of the rotor. That means you might want to climb out into the hub. You want to stop the turbine so you can do some work on it. That type of thing. Lock it out. Okay. All right, let's move down. What are the blades manufactured from?
Fiberglass.
Yep, that's an easy answer. Fiberglass epoxy resin. And we've all seen that when we have one of those blades. It's actually a Vestas blade, but it has fiberglass embedded into balsa wood with an epoxy resin and a gel coat. And what does the gel coat do? It says right there, blade color, UV protection. We're trying to keep the blade protected, and the gel coat tries to keep everything as aerodynamic as possible. All right. Let's move on now to question 14. I'm on question 14. Does the GE 1.5 use hydraulic or electric pitch motors? So when we read this, we're trying to understand that.
Electric.
Yep, electric. So we know that there is a motor that's going to spin the blade one direction or the other. And it's either going to be done by a hydraulic system or an electric system. So now we know that the GEs are using electric. Vestas tends to use hydraulic. Have you been in a turbine that's using electric blade pitch, Edwin?
No, everything is hydraulic.
Everything, they're just sticking with hydraulic. I wondered if they'd go back to it. I mean, hydraulic works. It's just messy,
Mm-hmm.
but it works.
Yeah, that's why they have messy towers.
Yeah. Yeah. Okay. So let's move on to question number 15. So question number 15 is saying, what protection do the blades and wind turbines have if grid power goes down and the turbine loses power? I mean, how does the turbine protect itself? Like if your house loses the grid, all the power's out. What is inside this turbine that's going to keep it to where it can keep running? Does anybody know?
Is it like what's it called? Blade break or
They
something that
do.
cuts off the generator from the blades?
Yeah. Well, what they do is they use those batteries. So your answer there would be each blade has a battery backup blade pitch system. So what that's going to do is it's going to use the batteries to feather the blades or to turn the turbine out of the wind so it's not spinning anymore. We don't want the blades to catch the wind because the grid's down and we're not making any power, or we don't want to do that. We want to shut our turbine down. So that's where that's at. Let's see. The next section is just talking about the hub. We already talked about the hub. The hub was that centerpiece of the wind turbine, the nose cone where all the blades are. That's where we have the pitch system and control systems. We'll learn more about that later. Each one of these areas will go into great detail, as much as I can go into anyway, throughout the year. So the next section we're looking at is the gearbox in the GEs. So it says the gearbox in the 1.5 60 hertz wind turbine is designed to function as a speed increaser and transmit power between the low RPM rotor. So remember, the rotor and the blades are only going 10 to 20 RPMs, and the high RPM electric generator. So the high RPM electric generator is running at a much faster speed, more like 1400 RPMs. But it's the gearbox that allows this to happen. So the gearbox for this turbine that we're talking about, 60 hertz, is a 3-stage planetary helical design with a gear ratio of 1:78. So what you want to write down on your question number 16 is the GE 1.5 has a 3-stage planetary helical design gearbox with a ratio of 1:78. Does anybody understand what any of that means?
We I don't know if everybody was in the last class, but when we
Yeah.
were going over gears, isn't it like how the gears not only how it's made, but how it spins and rotates?
Yeah. So like,
the 3-stage planetary has like 3 gears. No, actually it's 4. There's 3 gears that rotate around
yep,
one gear.
called a ring gear, right?
Yes.
And then the center gear would be
Planets rotating around a sun.
sun
like
gear.
Yes.
Yeah, good, excellent. Yeah, and the helical design is just the way that the teeth are cut. They're cut at a certain angle. And then the gear ratio ends up being 1:178. So 1:178 means that for every 1 rotation of the rotor, the generator is spinning 78 times, or so to speak. So that's what the ratio is. 78:1. Okay. So let's talk about bearings. Bearings are a really big important part of wind turbines. because they are really taking on an enormous amount of axial and radial loading, meaning that the wind's pushing on these blades from different angles, and that's forcing well, your bearing to wear out, right? So we're just going to write down. So in the last class, our 101 class, we learned about different types of bearings. And, you know, we had a very small introduction. So if you're like, I don't know anything about bearings, don't worry about it. Just try to learn them as you go, because we're not going to focus heavily. We're just focusing at this point in time on what is in this GE. So number 17 says the blade pitch bearing is a dual 4-point ball bearing. And the reason I point that out is because as a tech, you're going to have to learn the differences between different types of bearings. You know, is it a roller bearing? Is it a spherical double row, blah, blah, blah. There's several different types of bearings. You only are going to need to know, well, what kind of bearing is in the turbine I'm working on. Because then if it comes time for you to work on it or grease it or replace it, that's where it comes into play. Okay. Then we have a main shaft bearing. Main shaft bearing is another important bearing. Inside a GE wind turbine, the main shaft bearing is a double row spherical roller bearing. And it's mounted in a pillow block housing. So you can see all that information right here. Main shaft bearing is a double row spherical roller bearing mounted in a pillow block housing arrangement. We'll be coming back to this. We'll be looking at this bearing. We'll be looking at this pillow block housing. That's the big one. That's the big main bearing that's holding these blades to the nacelle. Okay. The next section, it has us moving on to the gearbox. Let's learn a little bit more about the gearbox lubrication system. Some of you guys don't know the information, but it's good to know. You've had these questions before. Let's back up here. Hold on. We missed a question. We're on question number 19. The gearbox bearing. I'm sorry. The gearbox uses roller bearings, and there's different ones. So these are 3 different types of bearings you're going to write down: cylindrical, tapered, and 4-point ball type. Cylindrical, tapered, and 4-point ball. Do you have to remember all this stuff? No. No, don't freak out like, I can't remember all this stuff. No, what you're doing is just becoming familiar with what this stuff is so we can have a conversation about them, just like we already are. Tyron and I have had a couple conversations about the gearbox. He was telling me about a ring gear and a sun gear and things like that you've already learned. That shows you that you're learning. That shows you you're getting ready to go into the next step. So what's important is these gearbox bearings alleviate the radial and axial loads that I just mentioned before, where the wind is blowing hard against the inside of the bearing can crack. You'll have blade bearings crack. You'll have these bearings have problems. They'll wear out. If there's balls or rollers inside them, they'll roll around in there, and the torque and the stress, the enormous torque, these things weigh 60 tons. You know, the blades weigh 60 tons. and the nacelle, they're pushing all this weight on these bearings. So they'll start to wear out from radial and axle loads. So that's answer to number 20. Okay, starts to get a little bit easier. We start to pick up a little speed here on some of these questions. A lot of the meat and potatoes of this brochure, we kind of talked about. So let's talk about the lubrication system. So the fluid capacity of the gearbox is 300 liters. 300 liters is how much oil that we've got to put inside that. And that's oil that's sprayed inside this gearbox as it moves around. So we'll look at drivetrain specifically in this class, and we'll see that there is a filter, there's a heat exchanger, there's different things that are within inside this gearbox that is trying to keep the temperatures regulated, because the viscosity of the oil matters. Is it too thick? Is it too thin? And also, is it got metal shavings in the oil? Do we have a problem with our teeth? Those are some of the maintenance things that we'll be looking for. Okay, so that would have been the answer to question number 2. So before the oil is pumped through the oil lines, passes through a filter, a heat exchanger, and a pressure reducer valve, which helps clean the oil and correct the pressure. At this point, we should be ready for section 3.8. So if you want to write that down in your notes, I'm going to be starting over with question number 1 under section 3.8. So what acts as the main braking system?
Blades.
Yeah, the blades. We have other brakes that can be incorporated, but when we talk about the main braking system, the main braking system is going to be those active pitch blades that take it out of the wind. So number 2, braking under normal conditions is accomplished simply by feathering. So the answer to number 2 is feathering. Feathering the blades out of the wind. That's normal braking. Number 3, we should know that answer already. Can the blades be feathered out of the wind if the turbine loses power due to grid? That should say grid line power loss. There's a couple typos maybe in there. If so, explain how. Well, we discussed that already, right? Each rotor blade has its own battery backup system that will feather the blades. Very good. Okay, so let's keep moving. We're around 9:49. The turbine is equipped with a mechanical brake located at the, all right, so now we're moving on to the brake system. So we have the electric pitch system right here. When we look at the next section, the turbine is equipped with a mechanical brake located at the output or high-speed shaft. So that's a great big brake caliper, just like on your car. That's generally at the high-speed shaft of the gearbox. And we only are incorporating this brake really when we have emergency situations and we're trying to stop the turbine from spinning so we can do maintenance. Okay. The next section is about the generator. And I like to talk about the generator a little bit because it creates certain issues in your understanding about whether or how these turbines work. So let's first establish a couple things. If I were to say synchronous, does anybody know what that means? The word synchronous means what?
Happening at the same time.
Correct. And asynchronous would be out of sync. Excuse me for a second. Happening at the same time. So this is telling us the generator is a doubly fed induction generator or an asynchronous generator is what it means. This is going to be a little more difficult to understand. Don't expect to fully understand everything that I'm saying at this point. You might, and you're more than welcome to ask more questions about it. I'll tell you as much as I know. So we need to understand this terminology here, doubly fed induction generator. Most of these turbines are going to have a doubly fed induction generator. This one has a wound rotor and slip rings. So the answer to number 6 is the generator is a doubly fed induction generator with a wound rotor. That's the type of motor it really is. A generator and a motor are pretty much the same thing. Like an electric motor and an electric generator are the same thing. So it has a round rotor and it has slip rings. Slip rings are something we're going to have to look at into greater detail, but slip rings are a big part of how this wind turbine works. So the next question is pretty simple. The generator's synchronous speed is 1200 RPMs. Does anybody know what that means?
Just 1200 revolutions per minute.
Yes, but you're correct. It means, well, it's 1200 RPMs, but it said the generator's synchronous speed is 1200 RPMs. So that's the answer to the question number 7. Number 7 is generator synchronous speed is 1200 RPMs. But what we just established, synchronous speed means moving at the same speed. But what the heck are they talking about? There's where it gets a little complicated. So let me just back up a little bit so you're not completely lost after this. Synchronous speed would be when the generator is making power at a perfect 60 hertz. That means it's running at a certain wind speed and the wind is blowing perfect. And now our turbine is making 60 hertz. But the problem is the wind doesn't blow at 60 hertz. The wind changes its speed. So if we don't have a drivetrain system like we have, or a doubly fed induction generator like we have to help us regulate the speed, then we're only going to be able to make power when this thing's running at 1200 RPMs. That's why the next question says a variable frequency power converter tied to the generator rotor. That's the part that allows the generator to operate at different speeds besides 1200 RPMs. It's this power frequency converter. It's these electronics that are going to help this wind turbine cheat a little bit and allow us to make power at slower and faster wind speeds at 60 hertz. So our range is going to be 870 RPMs on this particular turbine to 1600 RPMs. So question number 9, I explained that. I'll say it one more time. At 1200 RPMs, the generator's production voltage and current is at a perfect 60 hertz. It's synchronous with the grid. Synchronous with the grid. At 870 RPMs and 1600 RPMs, the wind turbine can still be synchronous with the grid, but only because we have a variable frequency power converter. And we don't really get into all the details of how a variable frequency power converter works until our 211 class, but we talk about it like we are now. Number 10, what is nominal speed for a GE 1.5 SLE? And what does that mean? Does anybody know?
The minimum amount of rotation for the blades to produce actual usable power.
That's its sweet spot. Yeah, it can still produce power at 870. It's just not very much. And it can produce power at 1600 RPMs, but that's as fast as that thing can spin. Once we start going faster than that, the turbine is going to start to pull itself out of the wind or shut down, like if we have too strong of winds. But it'll feather those blades to help slow it down. So even though it could maybe go faster, it'll rotate the blades so it doesn't. But nominal speed means if we want to make 1.5 megawatts, we need to be running at 1440 RPMs. That's what that's telling us. And what's interesting is 1440 RPMs is higher than synchronous speed. We don't want to run at synchronous speed if we can help it. We want to run higher than synchronous speed. I don't want to get into that too much. You're getting into things called sub or super synchronous on your generators. But at this point in time, we know that we can run in a range of RPMs. Now that's the generator spinning at those RPMs, not the blades. Remember, the blades are only moving at like 10 to 20 RPMs. Okay, so that should explain question 9. Should also explain question 10. Let's see. All right, so right here, the generator housing is grounded and it has an air-to-air thermal exchanger. Okay, so number 11 is the generator is air cooled, is what it's saying. It's air cooled and it has an air-to-air thermal exchanger. And that's cooling both, well, the generator windings, rotor stator. It's just keeping that motor, that generator cool. So it has these great big fans above it, above that generator, that are blowing air through there, that is blowing that off. So they're air cooled. Is the generator housing grounded? Yes, of course it is. It needs to be grounded. That's part of electrical. Okay. Next, temperature sensors are built into the generator windings to provide a temperature reading of the wind turbine controller to the wind turbine controller. So what we need to know is there's these great big meat thermometers that are all over the generator. They're on the bearing, they're on the windings. And what the temperature sensors do is they alert the wind controller to do an automatic shutdown if the temperature is outside the normal operating range. So for some reason, the generator is getting too hot. It could be the fan that cools it is not working. Additionally, the wind turbine will not start if the windings are below their acceptable operating temperature limit. So if things get too cold. All right. We are on question 15. And we're moving on to the flexible coupling. So the flexible coupling is in between the gearbox and the drivetrain. And it's designed to keep the torque below 3 times the nominal drivetrain torque. So that's your simple answer there. The flexible coupling limits the torque below 3 times the nominal drivetrain torque. What does a flexible coupling do? Does anyone know? It kind of says so in the name.
Does it help the blade to kind of rotate with the wind or keep it, kind of flexible? I guess.
Exactly. Yeah. So you have the gearbox and the generator, 2 different things, one in the other. In between the gearbox and the generator is a shaft. Now, that shaft is moving at 1400 RPMs. That thing's moving fast. We want it to be flexible enough to where that if it's out of control, it can actually tear itself apart, but it won't tear the entire wind turbine to pieces. It'll just destroy itself instead, and we'll have to put a new flexible coupling in. Or it helps in aiding with the vibrations that the turbine feels as we're moving between from the blades to the gearbox to the generator as we're going through these different shafts. So flexible coupling is a thing that we need to know what that is. All right, let's see here. We've got 17 more questions here and we're done. So we should be on section 3.11, yaw systems. So some of these questions get spread out a little bit further apart. We know that the yaw system is, let's see here. Yeah. Okay, 3.11. So a roller bearing is attached between the nacelle and the tower to facilitate yaw motion. Now we're talking about the top of the tower, the blades, the generator, the nacelle. The whole top of the tower will rotate north, east, west, or south 360 degrees. And there is another bearing there. and it's a roller bearing. So there's a roller bearing attached between the nacelle and the tower. So what we're learning is we've got bearings, we've got shafts, we've got flexible couplings, we've got these components that need maintenance. That's what we're learning. And we need to know that they're there so that we're aware of the parts that are going to wear out. You know, if you're driving down the road and you hear your wheels squeaking, you can't just go over there and kick it with your foot and hope it fixes itself. You got to understand that, well, it's squeaking because there's a bearing on that wheel, and that bearing on that wheel is wearing out, and I'm going to have to replace that before it completely wears out. That's called preventative maintenance. Let's talk about the yaw drives. 4 planetary yaw drives on this GE wind turbine. 4 planetary yaw drives with brakes that engage when the drive is enabled. So when we say planetary, that goes back to the fact that these yaw drives are these little motors that each have a little tiny gearbox on them as well. And in those gearboxes, we're going to have to make sure that there's oil, and we're going to have to make sure that they have gears and teeth that are not, you know, broke, chipped. And then we've got a motor that goes along with that as well. So number 2, under section 3.11, is you got 4 planetary yaw drives with brakes engaged when the drive is disabled. Okay. Let's move on to number 3. The automatic yaw brakes engage in order to prevent the yaw drive from drifting in turbulent winds. So let's just go with that. Number 3, the answer to number 3 is the automatic yaw brakes. So there's going to be some type of braking system that is usually like a caliper type system that can grab or push. It's an active system that will bite down and prevent the turbine from spinning. We'll have to look at that a little closer when we get to that. Number 4, a wind vane sensor is mounted on the top of the nacelle. That's answer to number 4. And it sends a signal to the turbine controller to evaluate the position of the nacelle with respect to the wind. So that should be pretty straightforward. So we've got a wind vane sensor, a turbine controller that is part of the PLC, the sensing system. This wind vane is telling the wind turbine's computer what direction the wind is coming from. So if the wind changes from north to south, that wind vane is going to know. If that wind vane isn't working properly, it's not going to allow your wind turbine to operate properly as well. Okay. Let's see here. Next question, number 5. The controller activates the yaw drives. So we have the wind vane going to the computer. The computer then tells the yaw drives to turn so many degrees this way to face the wind. And what we're looking for is the average wind direction. You know, we're not going to be chasing the wind constantly, but we're going to be looking for the average wind direction. All right, number 6. We already answered that one a little earlier, but the yaw drives require a electric power to operate. So the yaw drives are electric motors. All right, we're almost there for today. Number 7. What we're looking at is a cable twist switch sensor. Twist switch sensors are a little more confusing to understand, and I wouldn't expect anybody to know anything about those. But what we have is the wind turbine is going to rotate so many times before it can't spin anymore. It will tangle up its wires and everything will get all tangled up because it's still connected to wires. So what we have is a twist switch. So number 7 says a cable twist switch is mounted to provide a record of your nacelle position and how many times it's twisted. So cable twist sensor simply means if we've gone 360 degrees once, we've gone 360 degrees twice, it's not going to let us go a full 360 degrees again. It only will let you go 900 degrees, and then it's going to spin the turbine back out and reset. So usually that just happens over time as the turbine's chasing the wind, but it's a safety feature built in. So number 8, after the sensor detects a 900-degree rotation in one direction, the controller automatically brings the rotor to a complete stop, untwist the cable, and restarts the wind turbine. That's number 8. So if you were to explain number 9, you need to simply say something like the sensor is a limit switch and it's activated when it yaws 900 degrees in one direction or 2.5 turns, not 3 turns, but 2.5 turns. Then it reverses in direction and becomes untwisted or undamaged. Number 10, it's talking about the tower. So we're just going to make sure we understand what the rotor hub height is. It's 64 or 80 meters. That's how tall it is. We know that the tower is a tubular tower and they are tapered. They're bigger at the bottom. So if you're seeing them haul towers down the road, you'll notice that some are tapered or smaller at the top and they're bigger at the bottom. These are made from steel plates. So number 11 is the tower is tapered and manufactured in 3 sections. So the bigger the tower is, the more sections the tower is going to have. So 3 sections versus 5 sections. The really tall, big ones we were looking at earlier might be more than that. Number 12. It does have interior lights. So number 12 is just interior lights are installed inside the tower. when you're climbing to the top, those are important. Why? You're like, well, yeah, it's got lights. Well, you've got to work on those lights too. So sometimes you've got to change the light bulbs. Sometimes you've got to replace the light. They're on the side of the tower. You're going to have to be hanging off of a ladder in the middle of the tower, working on that, depending on where the light is. So you can't ignore those. Next section, 3.13. The nacelle. So the nacelle is constructed of fiberglass and lined with sound insulating foam. So number 13 is simply the nacelle is constructed of fiberglass. So that's what the white part of the turbine is, fiberglass, and they have an insulating foam. Sound insulating foam is to help keep them quiet because we don't want them to make any noise or bother the neighbors or bother anybody around them. Let's see here. Let's move on down to the next question. So let's see here. Getting ahead of myself a little bit. We're almost done. I think you guys had probably about enough. So number 14 is, and we've answered this question already earlier, but we're all the way down here. So when the rotor is stopped and secured in position with a hydraulic rotor lock, the interior of the hub can be accessed through one of the 3 hatches located in the hub or the rotor spinner. So we had talked earlier, Edwin said when he has to do that, he would go through three locks. And before he would 3 pins, pin it out. And we've got to look at that in detail. Okay, next question, number 14, only a couple more left. And we'll be able to you'll take a break. An anemometer, wind vane, and lightning rod are mounted on top of the nacelle housing. When you look at the top of these nacelles, you'll see these things that look like a cross or a lightning rod, which is exactly what they are. But we'll look at those when we see them in pictures, but there is a lightning rod up there. It is important because lightning protection is a huge part of wind. They do get struck by lightning more than we would like them to be struck. And if they do get struck, we're trying our best to make sure that the lightning goes to ground and not through our wind turbine electronic components, or as little as possible. So the rotor blades, number 15 says, the rotor blades are equipped with a strike sensor that's mounted in the tip of the blade. So when lightning strikes that blade, there is a little wire. I wouldn't say little, but it's about the size of, I don't know, your thumb. It's a cable that runs down that blade. It runs down into the grounding system of the tower. And it's there to try to send the lightning down the tower through the grounded system, as we already discussed. So to answer number 16, the system described in question 15 does what? It provides a grounding path that leads to grounding systems at the base of the tower. Simple as that. And the last question we have, we're not going to go into any more stuff. That's where we're going to stop. I'm gonna for your homework anyway, question number 17 is your last question. I think that's enough. But I feel like if you, let's just answer number 17. Number 17 says, even with a grounded system, can lightning damage the turbine? And that's a very easy answer. It should be yes, because we know lightning is an unpredictable force and it can cause damage to a variety of components, even with a lightning protection system. And that's one of the reasons why we have to get out of the tower. So I'm a little hesitant to talk about this, but I'm going to give it a try. So if you can see this picture, I want to try to explain to you in a very basic sense how this doubly fed induction generator works. You may not catch it all, but what we have is we have a transformer right here. This is at the bottom of the tower. That transformer is 34.500 volts. Okay, that's the grid. That transformer takes that power from the grid and steps it down to 575 volts. Still high voltage. But now we're at 2000 amps. This is a 2000 amp wind turbine. That's a lot of amps. And what happens is the grid comes up through the stator, and this is our generator. There's an invisible magnetic field that is spinning around this generator. So synchronous speed would mean that this thing's spinning at like 1200 RPMs. If you could see it, you can't see it, but it's going around. The rotor is the center part of the generator, and the wind is spinning this circle here. So what happens is the converter, as we mentioned before, has electronics in it that are going to rebuild the sine wave with pulse width modulation. They're going to take a sine wave. We haven't really talked about sine waves, but they're going to take a sine wave that looks erratic, wild. It's not a nice, smooth up, down, up, down. It's up real high, down real low. It's all over the place. That's because the wind is wild. So the wind is blowing this thing, but we're trying to capture as much of that wind as we can and keep this part of the turbine running between 870 and 1600 RPMs. If we're hitting 1400 RPMs, we're making 1500 kilowatts. That's what that means. And so our computer system can see the grid and see that it's running at 60 hertz. And then it can take that information with its computer system and make adjustments. And it does that by increasing or decreasing the magnetic field of the rotor. So again, we're getting way ahead of ourselves. Don't feel like, I don't understand any of this. We'll talk about the generator in greater detail, and we'll talk about how the rotor works in greater detail down the line. But for today, that's all we're going to do. So there's a little bit more information in here. You don't have to read all of it. You've got some pictures in here. You can see how the lightning protection system works. So if lightning were to strike here, it'll come down and it'll go down the tower and into the ground. We don't want it going through our components up here. But as long as you've completed your homework, which was basically just be with me today in a little study group like we did, answer some questions, show me that you've taken the time yourself to fill in the information so that you've processed some of those terminologies, some of those concepts in your head. You may not understand them all completely, but now you're getting a better idea of how a wind turbine works. what you would do then is once you finish this homework here, and I can click over to student view. You would come to this page here where it says start assignment. You'd click on that and you would do upload your file. So as soon as you're done with your homework, you just drop your file in there. Or you drop a picture or take a picture if you can. And you'll be done with this first assignment. Okay. I know that's not fun going through some of that stuff, and it's hard to understand when you don't have a lot of pictures, but we don't want to do too much on our first day. I just want to get you familiar with some of the terminologies. And I'm going to leave student view. Let's go back to modules. Now, we're not going to go through the fall protection stuff today because I think it'd be too much. It's a lot. We'll be working on that for a couple hours next class. But what I have in here is a link to a power performance report. This right here is something that I wouldn't expect probably none of you to really read, but I would hope you'd take a peek at it, because really all it is the National Renewable Energy Laboratory, which is in Golden, Colorado. That's a good place for some of you guys to get a job. If you want to get into research, you want to get into energy science and things, they have a lot of positions available at a variety of levels. They have technicians and they have scientists out there. So the National Renewable Energy Laboratory is kind of like NASA for renewable energy people. But they've taken this turbine and they tested it. They tested it in a real testing situation. And so they're a third party. You can read through some of this, but really what I want to do is watch your eyes. I'm scrolling. This shows you if I'm at a certain wind speed, this is how much this thing is making in kilowatts. So this is in meters per second. You'd have to convert it from meters per second to mile per hour if you want to understand that. And that's very easy. You just go to Google and type in meters per second to mile per hour calculator and pop in this number and you'll know what that is. You know, this right here, about 5.5 to 6 meters per second is about 10 mile an hour. So 10 mile an hour winds, this wind turbine is making 235,000 watts or so. But you got to remember the winds are much stronger at higher heights. And then when they get up into the higher range, this thing starts making closer to 1,500 watts, or what it can do for the max once it's getting past 10. So once it gets past 10 meters per second, it's pretty close to running at its full capacity. And that does beg the question, do these wind turbines run at full capacity all the time? And the answer is no. I wish they did, but they don't. They run as much as the wind blows. And, you know, it depends on who you ask and where the wind farm is. But, you know, some people say they run at about 50% on average of what they can do, 30 to 40% of what they can do. Then you have those windy days where they're just putting out a lot of power. But you also can look at this and see the cut-in wind speed is 3.5. Cut out wind speed means that this thing right here is the wind's too fast. And then you have your rated wind speed, which is your nominal speed. That's going to be our 1400 RPMs, 1440 RPMs. We want to be around 14.5 meters per second. This has basically the power curve. So you can see down here in the wind speed, as the wind speed increases dramatically, then we start to see the power go up. Okay. So I just wanted you to see that there is this document in here if you want to learn a little bit more. It's 55 pages long. It's a full report on this turbine. And I wouldn't expect you to read it at all. Just it's there if you want to look a little deeper into how these turbines work and the rating. So for today, that is all that I really have. Oh, I did want to point out this EIA map. So some of you guys that don't know about EIA maps, you just click on EIA maps. That can take you to this website here. And then you can click on here and let's zoom in. You can see all of the power plants. We'll remove the layers. We'll click on wind. And there you can see where all the wind farms are. Not all of them, but most of them throughout the United States. And you can zoom in even a little closer. And so for our area, you can see if you want to stay close to Indiana, you have all these wind farms here, all these wind farms in Illinois, and you even got some over in Ohio. So you can stay pretty close to Indiana if you want. If you don't want to stay close to Indiana, that's okay, because they've got wind farms all over the United States, and they're continuing to build them. So, is there any questions for me today before I let you guys go?
No.
Okay. Well, all I ask for you guys to do is to work on that. And those of you that I will be talking to at the 1 o'clock class, I'll see you guys at the 1 o'clock virtual course. If you are unable to make it, remember it's recording. So I will go ahead and stop recording here and I'll let you guys go. And I'll see you guys at 1 o'clock. If not, have a good weekend. See you soon.
See you soon.
See you, John.
See you later.
All right, see you guys.